Perhaps at this moment, you are in a very quiet place, a dark room, a late train, or a small town beneath a wide sky. Wherever you are, something remarkable is happening around you. The familiar laws of physics are still operating perfectly. Gravity keeps you attached to the ground. Electromagnetism is carrying this sound to your device, and the speed of light still maintains its value, regardless of which country or era you are in. That stability seems so familiar that we rarely stop to think about it. The world seems to always behave in an orderly way. Apples fall down instead of flying into the sky. Light travels according to rules that can be written as equations. Planets move along orbits that humans can predict centuries in advance. Electrons move according to neat mathematical patterns. The universe does not wake up each morning and suddenly decide to try a new set of rules. But if you think carefully, that stability itself is the strangest thing. Why does the universe have laws? Why do stable patterns exist instead of complete random chaos? For most of the history of science, physicists focused on determining what those laws are. Newton described gravity. Maxwell showed that electricity and magnetism are two aspects of the same phenomenon. Einstein turned gravity into the geometry of space-time. Then quantum mechanics revealed that beneath the familiar world lies a layer of reality where probability plays a central role. Each step helped us better understand how the laws operate, but beneath all of those achievements remains a deeper question. Not how the laws work, but why there are laws in the first place. Is the universe following some kind of command, or are the laws we talk about simply descriptions of the regularities we observe? They may be fundamental features of reality. They may also be patterns emerging from a deeper layer of structure that we have not yet seen. Whatever explanation is correct, one thing is clear: the existence of laws has brought stability to the universe. That stability allows atoms to form. Atoms lead to chemistry. Chemistry produces stars, planets, oceans, and eventually beings capable of asking questions about their own universe. Modern physics has begun to suggest that there may be deeper layers behind the familiar laws. Symmetries in nature appear to be closely connected to conservation laws. Quantum fields appear as if they are woven into the very structure of space-time. The constants of nature carry very specific values, and those values have shaped the entire history of the universe. Some cosmologists even speculate that many different universes may exist, where the laws could vary. Others suggest that the laws might emerge from deeper informational structures. Even so, even without knowing the final answer, there is something very remarkable. The universe can be understood. Its behavior can be described with mathematics. The same principles seem to apply across distances of billions of light years. This leads to an intriguing possibility. Perhaps the laws are not commands imposed upon reality, but the way reality exists at its most basic level: structure rather than command, pattern rather than regulation. In tonight's journey, we will move slowly through these ideas, from the history of discovering the laws of physics, to the role of symmetry in mathematics, then to quantum mechanics and cosmology, along with different philosophical interpretations of their nature. There is no shocking revelation waiting ahead, because sometimes the deepest mysteries of the universe do not appear as dramatic explosions, but exist quietly beneath everything familiar. The room around you feels solid because the laws of physics are stable. The device you are holding works because electromagnetic interactions are consistent. Your heartbeat depends on chemical reactions governed by quantum mechanics. And above the sky, the stars are still fusing hydrogen according to the same nuclear rules that have operated for billions of years. So the question is not whether laws exist. The question is why they exist. And when physicists talk about a law of physics, they are not referring to a set of rules written in the universe's rulebook. There is no parliament of particles voting to amend gravity. When physicists speak of a law, they do not imagine a set of rules that the universe must obey, like a legal code. The concept is actually far more modest. A physical law is simply a very compact way of expressing, often through mathematics, something that nature seems to do the same way every time. It records a regularity. When certain conditions appear, certain outcomes will follow. not because nature is listening to any command, but simply because that is how nature consistently behaves. This means that equations do not control the universe. They only describe the patterns the universe reveals. One of the clearest examples appeared in the late 17th century, when Isaac Newton introduced the law of universal gravitation. In its familiar form, the gravitational force between two objects is proportional to the product of their masses and decreases with the square of the distance between them. Written mathematically, this relationship is summarized in a short equation. The force equals the gravitational constant, multiplied by the first mass, multiplied by the second mass, divided by the square of the distance. With that compact expression, astronomers were able to calculate the motion of falling apples, the orbit of the moon, and the paths of planets around the Sunday. From very small irregularities in the orbit of Uranus, they even inferred the existence of a previously unseen planet, Neptune. Yet Newton's equation does not create gravity. It does not pull the Earth toward the Sunday. It is only a simplified summary of what humans observe in nature. A similar story unfolded in the 19th century with the work of James Clerk Maxwell. In 1865, Maxwell wrote a set of equations describing how electric and magnetic fields interact and propagate through space. When these equations were analyzed, they showed that disturbances in the electromagnetic field would travel at a specific speed. That number matched the previously measured speed of light. This led to a remarkable conclusion. Light itself is a form of electromagnetic wave. Those equations did not force light to exist. They simply revealed a deeper rule about how electric charges and magnetic fields behave. The beauty of Maxwell's work lies in the fact that a few compact mathematical relations linked seemingly separate phenomena, electrostatics, magnetism, and light, into a single picture. In the 20th century, the same pattern appeared again in quantum mechanics. In 1926, Erwin Schrödinger introduced an equation describing how the quantum state of a system changes over time. At first glance, its expression sounds quite abstract. An imaginary constant multiplied by the reduced Planck constant, and the time rate of change of the wave function equals the Hamiltonian operator acting on that wave function. But behind that complexity lies an extraordinary predictive power. The equation calculates the energy levels of the hydrogen atom with remarkable accuracy and provides the foundation for modern chemistry, semiconductor physics, and technologies such as magnetic resonance imaging. Yet it is still only a description. It does not command electrons to move in any particular way. It simply records patterns that have repeated across countless experiments, from the double-slit experiment to atomic spectroscopy. The difference between description and command is the key point. A physical law is not a rulebook the universe must consult. It is the way humans compress the stable regularities in the behavior of matter, energy, space, and time. There is another common misunderstanding that is also worth clarifying here. In everyday language, the word theory sometimes means a guess. But in science, a theory is a broad explanatory framework that covers many different phenomena. Einstein's general theory of relativity, published in 1915, explains gravity as the curvature of spacetime. Darwin's theory of evolution by natural selection explains the diversity of life. Within such theoretical frameworks, specific laws can exist. Newton's law of gravitation is part of Newtonian mechanics. Maxwell's equations belong to classical electromagnetism. Schrödinger's equation belongs to the theory of quantum mechanics. In other words, laws are usually concise mathematical relationships, while theories provide the conceptual picture explaining why those relationships exist. And when we ask why the laws of physics exist, what is really being asked is not why humans write equations. The deeper question is why the universe itself displays such stable mathematical regularities. Those regularities are tied to very specific numbers. The gravitational constant has a definite measured value. The electric charge of the electron is approximately 1.6 times 10 to the power of -19. The speed of light in a vacuum is about 300,000 kilometers per second. These numbers do not merely appear in textbooks. They seem to be woven into the very structure of reality. If their values were significantly different, stars might never form, chemistry might not function, and stable matter, at least as we know it, might not exist. The more closely we examine the laws of physics, the sharper the original question becomes. These laws appear to be stable patterns of nature, expressible as equations and applicable everywhere we have observed. They do not arise randomly. They are discovered through careful observation, repeated experiments, and mathematical reasoning. From the massive particle accelerators at CERN to the telescopes and satellites operated by NASA and the European Space Agency, scientists continually test whether these rules still hold under the most extreme conditions in the universe. Yet even when they work with great precision, a question quietly remains. Are these laws genuine features of reality, already present in the universe waiting to be discovered? Or are they merely models created by the human mind to compress vast amounts of data into elegant formulas? When Newton wrote the law of gravitation, did he uncover a deep structure of the universe, or simply produce a very efficient summary of the motions he observed? This is not merely a peripheral philosophical question. If the laws are discovered, it means the universe contains a mathematical structure that exists independently of any observer. But if they are only models, then perhaps what truly exists are individual events and interactions, while laws are simply the best way humans describe the patterns that emerge from them. The tension between these two perspectives has long existed in the philosophy of science. Some thinkers, following the view of David Hume, argue that laws are nothing more than the regularities we observe. Others believe that laws reflect deeper necessities built into the structure of nature itself. Modern physics, with its principles of symmetry and conservation laws, sometimes gives the impression that certain structures become almost unavoidable once basic assumptions are made. Whichever interpretation turns out to be correct, it is important first to understand what a physical law actually is. It is a precise summary, usually expressed in mathematics, of the repeating behaviors of the universe. It exists within broader theoretical frameworks, is continually tested, and can be revised when new evidence appears. And behind every equation, behind every successful prediction, there is always a quiet astonishment. The universe can be described mathematically at all. Its patterns are stable enough for humans to recognize, and reliable enough for us to depend on. In fact, for most of human history, the world was not viewed as a system governed by precise mathematical laws. It was seen as a living place, purposeful and sometimes unpredictable. Thunder was the voice of the gods. The motion of the stars carried sacred meaning. Stones fell because they sought their natural place, while fire rose because its nature belonged above. In ancient Greece, Aristotle constructed one of the most influential systems for explaining nature. In his model in the 4th century BCE, the universe was divided into two distinct realms. Below the moon was the world of change and decay. Above the moon was the perfect and eternal domain, where all motion was circular and uniform. Earth and water tended to fall downward. Air and fire tended to move upward. Celestial bodies moved in circles because of their perfection. These were not laws in the modern sense. They were explanations based on the nature and purpose of things. This system shaped European thought for nearly 2 millennia, partly because it seemed to fit everyday experience. Heavy objects appear to fall faster. The sky appears very different from the world beneath our feet. But within this view, there was almost no place for universal mathematical laws. The shift began slowly in the 16th century, when Nicolaus Copernicus proposed that the Earth orbits the Sunday. His model simplified certain astronomical calculations, though it still retained circular orbits and epicycles. It was more like a small tremor in thinking than a complete revolution. A deeper transformation came through observation. In the early 17th century, Galileo Galilei turned a telescope toward the sky and saw things that no one had previously observed so clearly. Mountains on the moon, moons orbiting Jupiter, and the phases of Venus. These discoveries weakened the rigid separation between the perfect heavens and the imperfect world below. The moon was not a smooth sphere. Jupiter had its own system of satellites. The sky was not fundamentally different from Earth as people had believed. Galileo also changed the way motion was studied. Through careful experiments with inclined planes, he showed that when air resistance is ignored, objects fall with the same acceleration regardless of their mass. More importantly, he realized that motion could be described with numbers. The distance a falling object travels increases with the square of time, when acceleration is constant. 1950. This idea was not only about falling objects. It marked a major shift. Nature could be described with precise mathematical relationships. Johannes Kepler, working from the extraordinarily detailed observational data of Tycho Brahe, discovered similar rules in the motion of the planets. He realized that their orbits are not circles but ellipses. The line connecting a planet to the Sun sweeps out equal areas in equal times, and the square of a planet's orbital period is proportional to the cube of its average distance from the Sunday. These laws were derived directly from data, not philosophical speculation. Kepler did not yet know why they were true, but what mattered was that the motions of the heavens could now be written as clear mathematical relationships. The culmination of this transformation came in 1687, when Isaac Newton published Philosophiae Naturalis Principia Mathematica. In that work, Newton unified the motion of objects on Earth and the motion of celestial bodies within a single theoretical framework. The force of gravity that pulls an apple toward the ground is the same force that keeps the moon in orbit around the Earth. No longer were there two different sets of physics for the heavens and the Earth. There was only one system of principles applying throughout the universe. And for the first time in history, the entire universe began to appear as a unified system governed by mathematical laws that operate everywhere. When Isaac Newton showed that the same gravitational force that pulls an apple to the ground also keeps the planets in orbit around the Sun, a profound shift occurred in how humans understood the universe. If two phenomena that seemed completely different followed the same principle, then perhaps all of nature was governed by similar universal laws. The scientific revolution gradually led to a new idea. The universe was not a chain of mysterious, disconnected events, but a system that could be understood through mathematics. Thinkers such as René Descartes, Gottfried Wilhelm Leibniz, and later Pierre-Simon Laplace began to imagine the universe as a vast machine. Laplace even proposed a hypothetical intelligence, a being that knew the exact position and velocity of every particle in the universe at a single moment. If such an intelligence existed, he argued, the entire future could be calculated in advance, and the entire past could be reconstructed. This image, often called Laplace's demon, reflected a growing belief in the determinism of natural laws. If the laws are exact and universal, then the universe should, in principle, to be predictable. This way of thinking gradually became a psychological assumption in modern science. Order came to be viewed as the default expectation. When a phenomenon did not match predictions, the response was not to abandon the idea of laws, but to search for deeper ones. The orbit of Mercury, for example, deviated slightly from Newton's predictions, but instead of discarding the concept of gravity, physicists continued investigating until Albert Einstein introduced general relativity in 1915, a theory that refined and expanded our understanding of gravity. Today, the expectation that every phenomenon has an underlying law seems completely natural. Yet this belief was not obvious from the beginning. It was built slowly over centuries through observation, experimentation, and reasoning. From the first telescopes and experiments with inclined planes to detailed astronomical tables, step by step, these efforts reinforced the idea that nature operates according to measurable patterns. This transformation carried with it a quiet strangeness. The night sky, once explained through mythology and symbolism, became the subject of precise calculations. A stone falling to the ground, once explained by the idea of a natural place, could now be predicted through gravitational acceleration. Order gradually became the default assumption. Even when science speaks of chaos, as in Edward Lorenz's chaos theory of the 20th century, that chaos still arises from deterministic equations. The flow of the atmosphere, the turbulence of fluids, and other complex dynamical systems may be extremely difficult to predict, but they still follow mathematical rules. The historical journey from Aristotle to Newton was therefore not simply about discovering a few isolated laws. It transformed the entire relationship between humans and nature. Qualitative explanations about essence and purpose were replaced by quantitative structures. The division between the heavens and the earth disappeared, replaced by universal principles that applied everywhere. And gradually, a new expectation formed. Behind every phenomenon there might exist a pattern that can be written in mathematics. Today this seems obvious, but it is the result of centuries of intellectual evolution. The universe never declared that it obeys laws. Humans gradually inferred this, tested it, and confirmed it again and again, until order became a foundational assumption of modern science. Beneath many modern physical theories lies another principle, one so subtle that it is sometimes overlooked because of its elegance. That principle is symmetry. In everyday life, symmetry suggests balance. Two halves of a face that resemble each other, or a snowflake that can be rotated around its center and still look the same. But in physics, the concept runs much deeper. A system is said to possess symmetry if a transformation can be performed, shifting position, rotating direction, or moving forward in time without changing the laws that govern the system. If the laws of physics today are the same as they were yesterday and will remain the same tomorrow, then nature has symmetry in time. If the laws are identical in London, Nairobi, or on a spacecraft orbiting Mars, then there is symmetry in spatial position. And if an experiment gives the same result whether it is rotated by 90 or 180 degrees, then there is rotational symmetry. These symmetries are not merely aesthetic, they lead to profound consequences. In 1918, mathematician Emmy Noether proved a famous theorem showing that every continuous symmetry of the laws of physics corresponds to a conserved quantity. If the laws do not change over time, energy is conserved. If they do not depend on position, momentum is conserved. And if they remain the same under rotation, angular momentum is conserved. This insight helps explain many familiar phenomena. A spacecraft drifting through space continues moving at a constant velocity because its momentum is conserved. A figure skater spins faster when pulling in their arms because angular momentum must remain constant. A cloud of gas collapsing during star formation rotates faster as its radius shrinks. Noether's theorem shows that conservation laws are not arbitrary rules added later. They arise directly from the symmetries of nature. Energy is conserved, not simply because we observe it, but because the universe does not treat different moments in time differently. Recognizing this connection changed how physics is constructed. Instead of beginning with forces and then writing equations of motion, modern physics often begins with principles of symmetry. In quantum field theory, the foundation of the standard model of particle physics symmetries determine which interactions are allowed to exist. The electromagnetic force emerges from a symmetry called U1. The strong nuclear force is associated with a more complex symmetry known as SU3. These symbols are simply mathematical ways of describing groups of transformations, but the core idea is clear. The structure of forces is constrained by symmetry. Even Einstein's general relativity rests on a similar principle, known as general covariance, the requirement that the laws of physics retain the same form under all smooth coordinate transformations. From that symmetry requirement, the description of gravity as the curvature of space-time emerges almost inevitably. In this way, symmetry becomes a guiding principle. Instead of observing forces and then summarizing them, physicists sometimes begin by asking, what symmetries does nature respect? From there, the mathematical consequences gradually unfold. And this opens an intriguing possibility. Perhaps the laws of physics look the way they do simply because they must, once certain symmetries are assumed, like inevitable consequences of a deeper structure. If a perfect sphere were placed before you, you could rotate it in any direction, and its shape would remain unchanged. That symmetry itself limits the forms it can take. In physics, the laws of nature face similar constraints. If the universe does not distinguish between yesterday, today, and tomorrow, then the equations that describe motion must retain the same form when time is shifted. The laws that can exist are therefore not unlimited. They are restricted by the invariant conditions of nature. Of course, symmetry in physics is not always perfect. In the very early history of the universe, many physicists believe that the forces we know today were once unified into a single interaction. As the universe cooled after the Big Bang, some of these original symmetries were broken. This spontaneous symmetry breaking, through the Higgs mechanism, gave particles their mass and allowed different forces to emerge from what had once been a more unified state. Even here, symmetry breaking does not mean chaos replacing order. It is a structured transition, still guided by deeper symmetry principles. Symmetry also lies at the heart of special relativity. One of the key assumptions Albert Einstein introduced in 1905 was that the laws of physics must be the same for all observers moving at constant velocity. From this requirement of symmetry, an unexpected consequence follows. The speed of light, in a vacuum, must be identical in all inertial frames of reference. From this arise the familiar effects of relativity, such as time dilation and length contraction. These are not minor details, they are direct consequences of a symmetry principle. Because of this, the way questions are asked also changes. Instead of asking why energy is conserved, one might ask why time does not privilege any particular moment. Instead of asking why momentum persists, one might ask why space does not select a special location. The answers return to the same idea, the invariance of physical laws under transformations. This suggests that the form of the laws of physics may not be arbitrary. They may reflect deep structural features of reality. The universe seems indifferent to where, when, or in which direction an experiment is performed. And it is precisely this indifference that appears as conservation laws and stable dynamics. Yet this still does not answer the ultimate question. Why does the universe possess such symmetries in the first place? Why do the laws remain unchanged under these transformations? Those questions remain open, but at the very least, symmetry provides a powerful organizing principle. Instead of countless disconnected rules, much of physics may follow from only a small number of symmetry requirements. Behind many familiar laws, there may not primarily be forces or matter, but invariant patterns, structures that remain the same when viewed from different perspectives. A universe that does not distinguish between places or moments naturally gives rise to conservation laws. In this sense, symmetry may not only shape the laws of physics, but also explain why they exist in a structured form. This idea leads to another question, equally strange. In 1960, the physicist Eugene Wigner wrote a famous essay titled "The Unreasonable Effectiveness of Mathematics in the Natural Sciences." He raised a simple but profound question. Why do abstract mathematical structures, sometimes developed with no intention of application, describe the physical world with such remarkable accuracy? Mathematics often begins as a game of pure thought. Complex numbers were once considered strange ideas because they involved the square root of negative numbers, a concept with no direct image in everyday experience. Yet these very numbers lie at the heart of quantum mechanics. The Schrödinger equation cannot exist without them. Remove complex numbers, and the entire modern description of atomic structure collapses. A similar story occurred with non-Euclidean geometry. In the 19th century, mathematicians such as Bernhard Riemann and Nikolai Lobachevsky wondered what would happen if Euclid's parallel postulate were changed. At the time, this seemed like nothing more than an intellectual exercise. Yet a few decades later, Einstein used that very geometry to describe the curvature of space-time in general relativity. Mathematics seemed to exist beforehand, waiting for physics to make use of it. Sometimes the agreement between mathematics and the physical world becomes astonishing. In quantum electrodynamics, developed by Richard Feynman, Julian Schwinger, and Shinichiro Tominaga, theoretical calculations predict the magnetic moment of the electron with accuracy exceeding 10 decimal places. The agreement between calculation and experiment at that level of precision is truly remarkable. How should this be understood? Some philosophers and mathematicians, following a Platonic perspective, argue that mathematical entities exist independently of humans. In this view, numbers, geometric forms, and algebraic structures are not invented, but discovered. They exist in an abstract realm beyond space and time. If this is true, the effectiveness of mathematics is not mysterious at all. The universe itself may have an inherently mathematical nature. Physical laws would then simply be expressions of deeper mathematical truths. Another view, known as nominalism, argues that mathematics is only a tool created by humans to describe the world. From this perspective, mathematics is effective simply because it has been refined over time to fit observational data. Equations that successfully describe reality are kept, while those that fail are discarded. Between these positions lies an intermediate perspective, often called structural realism. According to this view, science may not capture the intrinsic nature of things, but it does capture the structure of the relationships between them. Mathematics is effective because it reflects that relational structure. This leads to an even deeper question. Does mathematical structure exist first, with physical laws emerging as its expression? Or do the laws of the universe themselves create the patterns that mathematics later describes? One possibility is that the universe possesses an intrinsic mathematical architecture. In that case, the simplicity of many physical laws reflects a deeper simplicity at the core of nature. For example, the law of universal gravitation can be described as follows. The gravitational force between two objects equals a gravitational constant multiplied by the mass of the first object, multiplied by the mass of the second object, and divided by the square of the distance between them. The elegance of this relationship may not be accidental. It reflects the fundamental geometry of three-dimensional space. Another possibility begins with humans themselves. We evolved in a world where laws are relatively stable. Brains capable of recognizing patterns offered a survival advantage. From those pattern recognition abilities, mathematics gradually developed as a refined language for describing the regularities that nature had already displayed. Over time, the human capacity for abstract reasoning continued to develop. Mathematics became increasingly sophisticated, and one common explanation for the close fit between mathematics and physics is that the human brain has adapted to an environment with stable structure. In a world where recognizing recurring patterns offered a survival advantage, the ability to detect regularities gradually evolved. From these abilities, mathematics developed as a tool for describing patterns that nature had already displayed. Yet this explanation still seems incomplete. The mathematics used in modern physics goes far beyond anything that everyday intuition could suggest. Tools such as tensor calculus, Hilbert spaces, group theory, and topology are not survival skills for navigating the natural environment. They are deeply abstract structures, yet they precisely describe phenomena such as black holes, elementary particles, and the expansion of the universe. So the question returns, why can the laws of physics be expressed in such elegant, mathematical forms? This elegance is not a minor detail. For example, Einstein's field equations, which describe how energy and momentum curve spacetime, can be written in a single line of mathematical symbols. When expressed in words, the core idea is quite simple. The curvature of spacetime is proportional to the amount of energy and momentum present in a region. Yet this compact relationship governs enormous phenomena, from the bending of starlight as it passes near the sun to the expansion of the entire universe. Another example is the Schrödinger equation in quantum mechanics. Although it appears abstract, this equation accurately predicts the spectral lines of the hydrogen atom. Those spectral lines have been measured in laboratories and also observed in the light emitted from stars billions of light-years away. Remarkably, the same mathematical relationship holds everywhere. Examples like these suggest that the universe may be built upon a relatively small set of fundamental rules. The complexity we observe in nature could emerge from the combination and interaction of those basic rules. Yet this elegance deepens the mystery. The universe does not merely exist, it is understandable. It can be analyzed through reason, observation, and mathematics. And this capacity for understanding does not seem limited to a small corner of reality. It stretches from the motion of galaxies to the behavior of electrons. One can imagine a different kind of universe. A universe where patterns exist but are too unstable to compress into equations. A universe where every event requires its own rule. In such a world, prediction would be nearly impossible, and science as we know it could not exist. But the reality we observe is different. It exhibits remarkable consistency. Symmetry principles lead to conservation laws. Differential equations describe the motion of objects. Probability amplitudes predict outcomes in quantum mechanics. Mathematics does not merely approximate the behavior of nature in many cases. It describes it with astonishing precision. The debate over whether mathematics is invented or discovered may never be fully resolved. Perhaps both perspectives contain part of the truth. Humans create symbolic systems and abstract languages. Yet sometimes those systems reveal structures that feel as though they had always existed, waiting to be recognized. What cannot be denied is the striking correspondence between mathematics and the physical world. The patterns of the universe are not chaotic strokes. They possess structure, and that structure can be expressed through mathematical relationships. Whether this reflects a Platonic realm of mathematics, a structural feature of reality, or simply a language refined over time, the outcome is the same. The laws of physics are written in mathematics because mathematics, in some deep sense, fits the world. And it is precisely this natural fit that sometimes makes us forget the original mystery. Why is reality understandable at all? We often imagine the laws of physics as invisible rules imposed upon matter. Gravity commands the moon to orbit the Earth. Electromagnetism tells electrons how to move. The Schrödinger equation dictates how quantum states evolve. This language feels natural because it resembles how human societies operate. Laws are written, enforced, and used to regulate behavior, but nature does not receive instructions. An electron does not consult Maxwell's equations before responding to an electric field. A planet does not check Newton's law of gravity before moving through space. Equations are simply the way humans describe what consistently happens. They are not the cause of those events. This distinction may seem small, but it fundamentally changes the way questions are framed. If laws are commands, we might ask who or what enforces them. But if laws are descriptions, the question becomes different. The universe does not obey laws. It simply behaves according to stable patterns, and those patterns can be expressed mathematically. The philosopher David Hume in the 18th century articulated this idea clearly. According to Hume, what we call laws of nature are simply regularities in experience. When one type of event is consistently followed by another, the human mind forms an expectation. For example, when water is heated under standard atmospheric pressure, it boils at about 100 degrees Celsius. After observing this repeatedly, we expect it to continue happening. In Hume's view, there is no invisible necessity forcing it to occur. It is simply that, so far, under those conditions, it always has. From this perspective, laws are summaries of the entire pattern of events in the universe. They do not govern reality from outside it. They merely reflect how events are actually distributed in space and time. This view later became known as the Humean perspective on laws. The philosopher David Lewis further developed it by suggesting that laws are principles of the best system, a system that balances simplicity with explanatory power. Not everyone agrees with this interpretation. Non-Humean views argue that laws are more than summaries. They reflect necessary connections in nature. Some philosophers suggest that laws express relationships between universal properties. Others propose that entities possess intrinsic dispositions or powers. In this view, mass, for instance, carries a tendency to attract other masses. Gravitational interaction is not merely an observed pattern. It reflects a real power present in nature. These two perspectives lead to different interpretations of the original question. If laws are deep necessities embedded in reality, then asking why they exist becomes a profound metaphysical problem. But if laws are simply summaries of observed regularities, the focus shifts elsewhere. Why are the patterns of the universe themselves so stable? Consider again the example of energy conservation. In laboratories on Earth and in particle collisions at CERN, the total energy of an isolated system is always observed to remain constant over time, within the limits of measurement accuracy. This observation can be expressed simply. The total energy of a closed system does not change with time. From a Humean perspective, this is merely a generalization of repeated observations. But from another perspective, the principle reflects a deeper necessity connected to the symmetry of time, as Noether's theorem suggests. Despite different philosophical interpretations, the mathematical structure of the law remains the same. Viewing laws as descriptions rather than commands softens the original question. There is no need to imagine some cosmic mechanism enforcing them. It is enough to acknowledge that nature exhibits stable patterns that can be written as equations. Yet even from this perspective, the deeper question remains. If laws are only descriptions, then the stable regularities of the universe themselves demand explanation. Why is the behavior of nature consistent rather than random? Why do conservation principles hold across billions of light years? And why does an equation like the Schrödinger equation predict atomic spectra with such precision? Humean philosophy reminds us that laws do not float outside reality, but the patterns they describe remain, and those patterns are the deeper mystery. When we look at the physical world, it is easy to feel that the laws of nature are like immutable commands. But in reality, what we call laws may simply be descriptions of patterns that the universe repeatedly displays. There is no rulebook being consulted. The universe simply operates, and in doing so, recurring structures appear before us. Some principles seem too fundamental to question. Energy is conserved. Momentum does not simply vanish. The speed of light in a vacuum retains its value. These facts easily lead us to believe that they lie at the deepest layer of reality, beyond further reduction. Yet the history of physics has repeatedly shown that this intuition can mislead us. In many cases, laws that appear fundamental actually emerge from the collective behavior of countless smaller interactions. This idea is known as emergence, the appearance of macroscopic properties arising from microscopic processes. A single water molecule does not have a temperature. Temperature only becomes meaningful when trillions of molecules move together. Pressure is similar. It is not a property of an individual particle, but the result of innumerable microscopic collisions. Thermodynamics provides the clearest example. In the 19th century, scientists such as Sadi Carnot and Rudolf Clausius developed laws describing the relationship between heat, work, and entropy. Among them, the second law states that the entropy of an isolated system tends to increase over time. This law explains why heat flows from hot objects to cold ones, why ice melts in a warm room, and why perpetual motion machines of the second kind are impossible. But Ludwig Boltzmann introduced a radically different perspective. He showed that the laws of thermodynamics are not absolute commands of nature but statistical consequences of the motion of enormous numbers of microscopic particles. A box of gas may contain roughly 10 to the power of 23 molecules. No one can track each molecule individually, but statistical mechanics allows their collective behavior to be described by simple laws. Boltzmann's famous entropy formula relates entropy to the number of microscopic configurations corresponding to a macroscopic state. In other words, a state with high entropy is simply one that can be arranged in many more microscopic ways. Within this framework, the second law is not an absolute prohibition. It is simply something that is overwhelmingly likely to occur. In principle, heat could flow spontaneously from cold to hot. But the probability of such an event is so small that it would not occur even over the lifetime of the universe. From this emerges an intriguing possibility. If laws once considered fundamental, like thermodynamics, actually arise from deeper mechanisms, then perhaps the laws we currently regard as fundamental may themselves emerge from even deeper layers of structure. In condensed matter physics, this idea is not speculation, it is everyday reality. When certain materials are cooled below a critical temperature, they enter a superconducting state in which electrical current can flow without resistance. This phenomenon cannot be understood by examining a single electron. According to the BCS theory of 1957, electrons pair up into Cooper pairs and move coherently through the crystal lattice, producing entirely new effective laws of behavior. Another remarkable phenomenon was discovered in 1982 at Bell Laboratories, the fractional quantum Hall effect. Under extremely strong magnetic fields and very low temperatures, electrons in a two-dimensional system behave collectively in a way that produces quasi-particles carrying fractional electric charge. Fractional charge does not exist at the level of individual electrons. It emerges only when the entire system behaves as a collective state. These new laws are not illusions. They are measurable, precise, and stable, yet they are not the most fundamental rules of nature. This suggests that nature may be organized in layers of structure. At one level, quantum field theory describes elementary particles. Above that, atomic physics describes atoms. Then comes chemistry with molecular bonds, followed by biology with complex living systems. Each level possesses its own effective laws. The physicist Philip Anderson summarized this idea in a famous phrase: "More is different." As complexity increases, new organizing principles appear, principles that cannot simply be reduced to those at lower levels. If this is true, the question of whether physical laws are fundamental or emergent becomes far more subtle. Some laws, such as the conservation of energy, may arise from deep symmetries of nature. Others, like the second law of thermodynamics, clearly emerge from statistical behavior, and emergence may extend even further. Some approaches in quantum gravity, including string theory and loop quantum gravity, raise the possibility that space-time itself may not be fundamental. The geometry of space might instead be a large-scale manifestation of deeper quantum structures. The holographic principle, inspired by the study of black hole thermodynamics by Jacob Bekenstein and Stephen Hawking, suggests that the information contained within a region of space may be encoded on its boundary surface. This idea opens the possibility that geometry itself is not a primary ingredient of reality. Research groups at institutions such as the Perimeter Institute and the Institute for Advanced Study are exploring whether space-time and gravity might emerge from patterns of quantum entanglement. If this turns out to be true, then even Einstein's field equations may only be effective descriptions at large scales, and even the Standard Model of particle physics, though extensively confirmed at CERN's Large Hadron Collider, may itself be only an effective theory because it contains parameters that appear arbitrary, such as particle masses and interaction constants. Some theorists have begun to suspect that the laws we commonly call fundamental may not be the final layer of explanation. It is possible that they are only the surface of a deeper structure, a theoretical framework that science has not yet fully uncovered. If that is the case, the familiar question about the laws of the universe must be reframed. Instead of asking why the universe has exactly these laws, we might ask what deeper level of reality gives rise to them. Seen this way, the laws are no longer absolute foundations. They become layers of description stacked upon one another. It is important to note that emergent does not mean fragile. The second law of thermodynamics still operates reliably in every engine and every star. Superconductivity can still be measured precisely in laboratories. Conservation principles remain stable and consistent. They do not become weaker simply because they might originate from deeper mechanisms. This perspective makes the laws of physics more flexible in philosophical terms. Instead of imagining a single, unchanging foundation, reality may resemble a hierarchy of effective descriptions. Each level is valid within its own domain. The deepest layer, if such a layer exists, remains unknown. It could be a purely mathematical structure. It could involve informational constraints. It could consist of quantum fields, or it might be something that science does not yet even have the language to imagine. The history of physics suggests that we should be cautious before declaring any layer the final one. Yet even if the laws of physics are fixed and universal, they are still not sufficient to describe the entire universe. A law tells us how a system evolves. but it does not tell us where the system began. In classical mechanics, Newton's laws describe how the position and velocity of an object change when forces act upon it. However, they do not say where the object initially was or how fast it was already moving. Without that starting information, the future of the system cannot be calculated. Those starting values are called initial conditions. This distinction becomes especially important when we consider the entire universe. The Big Bang model describes the large-scale evolution of the cosmos. It is based on Albert Einstein's theory of general relativity and the assumption that, on very large scales, the universe is homogeneous and isotropic. The Friedmann equations, derived from Einstein's field equations, show that the rate of expansion of the universe depends on the density of energy and the curvature of space. These equations describe how the size of the universe changes over time, its expansion, its possible slowing, or even the possibility of eventual collapse. But the equations themselves do not tell us what the universe looked like at a particular moment. To determine that, we need initial conditions. In the 1920s, Georges Lemaitre proposed that the universe was expanding from a denser state in the past. He called this initial state the primeval atom. Only a few years later, Edwin Hubble's observations in 1929 showed that distant galaxies are moving away from us with speeds proportional to their distance, strong evidence that the universe is indeed expanding. In this picture, the laws lie in the dynamics of expansion. The initial conditions lie in the early universe's energy density, temperature, and distribution of matter. An important clue comes from the cosmic microwave background radiation discovered in 1965 by Arno Penzias and Robert Wilson. Measurements show that the early universe was extremely uniform, with temperature fluctuations of only about 1 part in 100,000. Those tiny fluctuations, under the influence of gravity, gradually grew into the galaxies and galaxy clusters we observe today. The laws of gravity determine how the fluctuations grow, but the pattern of the initial fluctuations determines which structures form and where. The laws shape how the process unfolds. The initial conditions shape the specific story that unfolds. A simple analogy is a game of chess. The rules of the game are fixed and universal, but the initial arrangement of pieces determines the opening position. From the same set of rules, countless different games can unfold. Cosmology works in a similar way. Without laws, there is no consistent evolution. But without initial conditions, there is no specific universe to evolve. This combination also clarifies certain philosophical questions. When we ask why the universe has these laws, we are asking about the equations governing dynamics. When we ask why the universe has the large-scale structure we observe today, we are often asking about the initial conditions. One striking example involves the fine-tuning of the early universe's matter density. Its value appears extremely close to the so-called critical density, the boundary between two scenarios, a universe that eventually collapses and one that expands forever. If the initial density had differed even slightly, cosmic history might have unfolded very differently. Another mystery concerns the arrow of time. The second law of thermodynamics states that entropy tends to increase. But for entropy to increase, it must begin in a relatively low state. Observations of the early universe suggest that it started with extremely low gravitational entropy compared with what was possible. Why this was the case remains uncertain. Some models propose cosmic inflation, a phase of extremely rapid expansion suggested by Alan Guth in 1981. Inflation could smooth out irregularities and make the universe more uniform. Yet inflation itself requires certain initial conditions in order to begin. Seen this way, explanations of the universe appear to involve multiple layers. The laws tell us how change occurs. The initial conditions tell us what exists to change. If the laws were chaotic or inconsistent, even simple initial conditions could not produce a stable universe. Conversely, if the initial conditions were completely random, even the most elegant laws might struggle to generate lasting structure. A universe with order requires both consistent dynamical rules and a specific starting point. This makes the question more subtle. Why do the laws exist? And why did the universe begin in that particular initial state? The two questions are related, but they are not the same. The laws describe the possible paths the universe could take. The initial conditions determine which path is realized. Together, they give rise to stars, galaxies, planets, and eventually to beings capable of reflecting on the universe itself. And if we were to point to one candidate for the most fundamental description of nature at the energies accessible to us today, modern physics would often point to the standard model of particle physics, the theoretical framework developed in the second half of the 20th century to describe elementary particles, and three of the four fundamental interactions of nature. In the second half of the 20th century, physics developed a powerful theoretical framework for describing matter at its most fundamental level. This framework is known as the Standard Model of Particle Physics. It describes three of nature's fundamental interactions: the electromagnetic force, the weak nuclear force, and the strong nuclear force. Only one force remains outside this picture: gravity, and its absence continues to be an unresolved problem. At the center of this model lies quantum field theory. In this view, the universe is not made of tiny solid particles flying through empty space. Instead, space is filled with fundamental fields. What we call particles are simply localized excitations, ripples in those fields. An electron is not a tiny microscopic sphere. It is a disturbance in the electron field. A photon is a vibration of the electromagnetic field. Each type of particle corresponds to a field that extends throughout the universe. Quantum field theory combines the two pillars of modern physics, quantum mechanics and special relativity. It ensures that no influence travels faster than light while describing physical processes through probabilities and quantum amplitudes. Yet the deeper structure of the Standard Model rests on another principle: gauge symmetry. These symmetries are not rotations in space or shifts in time. They are mathematical transformations within the fields themselves, changes that leave physical predictions unchanged. Remarkably, when the equations are required to respect these symmetries, the fundamental forces appear as a consequence. In electromagnetism, the relevant symmetry is called U1. When the electron field undergoes a specific phase transformation, the equations remain consistent only if the electromagnetic field transforms accordingly. This requirement leads directly to the existence of the electromagnetic interaction. Other forces are associated with their own symmetry structures. The weak force is connected to the group SU2. The strong force, the interaction that binds quarks tightly inside protons and neutrons, is described by the symmetry SU3. These symbols represent mathematical groups that describe how internal transformations operate within the fields. In the 1960s, Sheldon Glashow, Abdus Salam, and Steven Weinberg developed the electroweak theory, which unified the electromagnetic force and the weak force within a single framework. Later, quantum chromodynamics, QCD, described the strong force through interactions between quarks and force-carrying particles known as gluons. The predictions of these theories have been tested repeatedly in particle accelerators. At CERN, the Large Hadron Collider, LHC, accelerates protons to energies of trillions of electron volts and collides them at nearly the speed of light. Enormous detectors such as ATLAS and CMS analyze the debris from these collisions to compare experimental results with theoretical predictions. A major milestone occurred in 2012 when CERN announced the discovery of the Higgs boson. The Higgs field had been proposed in the 1960s as a mechanism that allows particles to acquire mass while preserving gauge symmetry. When particles interact with this field, the strength of their interaction determines their mass. The Higgs boson is the quantum excitation of that field. Its discovery confirmed that a process known as spontaneous symmetry breaking occurs in the electroweak part of the theory. At very high energies, the electromagnetic and weak forces are actually unified. As the universe cooled after the Big Bang, the symmetry broke, and the two forces became distinct. The Higgs field settled into a non-zero value throughout space, giving mass to particles such as the W and Z bosons. All of this structure can be summarized in a mathematical expression known as the Lagrangian of the Standard Model. When written fully in symbolic form, it occupies only about a page. Yet within that compact expression lies a complete description of how fermions such as quarks and leptons interact with the gauge fields of the three fundamental forces and with the Higgs field. However, even in its success there is something striking. Many parameters in the model appear to be arbitrary. The electron's mass is about 0.51 mega-electron volts. The top quark's mass is about 173 giga-electron volts. The strength of the strong force is described by a coupling constant that changes with energy scale. Altogether, the Standard Model contains more than 20 free parameters. These values are not predicted by the theory itself, they must be measured experimentally. This leads to deeper questions. Why do these constants have exactly those values? Why are there precisely 3 generations of quarks and leptons? Why does the Higgs field have its particular vacuum value? And why do quarks never appear in isolation but are always confined inside larger particles, a phenomenon known as color confinement? From one perspective, the Standard Model is a triumph of reductionism. It explains processes ranging from nuclear reactions in the cores of stars to radioactive decay using a small set of fundamental fields and symmetries. But from another perspective, it introduces a new mystery. If physical laws arise from symmetry, why did the universe choose these particular symmetries, U1, SU2, and SU3, rather than some different structure? Some theories, such as grand unified theories, GUTS or string theory, attempt to embed the Standard Model within a larger symmetry framework. They suggest that at extremely high energies, perhaps near the Planck scale, the forces of nature may be unified even more deeply. So far, however, experimental evidence for such ideas has not yet appeared. For this reason, the Standard Model is both a destination and a signpost. It shows that many physical laws can be derived from symmetry principles within quantum field theory. At the same time, the existence of unexplained parameters suggests that the current structure may only be an effective description. The question therefore returns once again: are these laws truly fundamental, or are they expressions of a deeper theory that we have not yet discovered? The Standard Model does not explain why the laws exist. It only clarifies the content of those laws at the energy scales humans can currently observe. It shows that matter is governed by quantum fields and symmetry principles. Yet even within its precision, there remains a gap, a quiet space, where the deeper question persists. Why does the universe have this structure rather than another? And long before these questions had a chance to find answers, physics had already experienced another dramatic turning point. In 1915, Albert Einstein completed a theory that completely transformed how humans understood gravity. For more than 2 centuries before that, Isaac Newton's law of universal gravitation had described the attraction between objects as an instantaneous force acting across space, a model that worked with remarkable accuracy for planets, tides, and moving objects on Earth. At the beginning of the 20th century, a major question about gravity remained unresolved. Why does the orbit of Mercury experience a precise precession that cannot be explained by existing theories? Albert Einstein approached this issue from a completely different perspective. Instead of asking how masses influence each other through space, he asked how matter and energy themselves could affect the fabric of space-time. The result of this thinking was the theory of general relativity, a theory that completely changed the way we understand gravity. At the core of this theory is a completely new idea. Gravity is not a force, as we once thought. It is simply the manifestation of the curvature of space-time. Objects with large masses, like stars and planets, bend the geometry of the surrounding space-time. Other objects move along trajectories defined by this curvature. To understand this shift, we need to clarify the concept of space-time. In the special theory of relativity, published by Einstein in 1905, space and time were no longer 2 separate entities but were unified into a 4-dimensional continuum. An event is described not just by three spatial coordinates but also by a time coordinate. General relativity extends this concept. It asserts that space-time is not a fixed backdrop. It can bend, stretch, and change under the influence of matter and energy. To describe this bending, we use the mathematical language of differential geometry, particularly the work of Bernhard Riemann. The Einstein field equations, the central equations of this theory, can be expressed simply. The curvature of space-time is proportional to the energy and momentum within it. This is not a metaphor. It is a precise mathematical statement tested by real-world observations. For example, when light passes near the sun, its trajectory is bent slightly because the space-time around the sun is curved. This event was first confirmed during the 1919 solar eclipse, when Arthur Eddington's expedition measured the deflection of light from stars near the sun, exactly as predicted by Einstein's equations, not by Newton's gravitational force. Another phenomenon that illustrates this difference is gravitational time dilation. A clock placed on top of a mountain will run faster than a clock at sea level. This effect has been measured with extremely high precision using atomic clocks. In fact, the current GPS system, which allows satellites to determine positions accurately, must account for both the effects of special relativity and general relativity. Without these adjustments, the positioning errors would increase by several kilometers each day. Within the framework of general relativity, freely falling objects are not being pulled by a force. Instead, they move along geodesics, the straightest paths in curved spacetime. Just as a great circle is the shortest path on the surface of a sphere, a geodesic is the natural path in curved spacetime. This geometry completely changes the way we view motion. The movement of planets around the sun is not the result of a force acting across empty space. It is the natural consequence of moving through a curved geometry. Earth moves along a geodesic in space-time shaped by the mass of the Sunday. This discovery leads to a profound realization. The behavior of matter cannot be separated from the structure of space-time itself. The laws of motion are not imposed from outside the geometry. They are encoded right within the geometry. Black holes are the most extreme example of this. When a star with enough mass collapses under its own gravity, the curvature of space-time becomes so intense that nothing, not even light, can escape from within the event horizon. Schwarzschild's solution to the Einstein field equations precisely describes this geometry. The radius of the event horizon is proportional to the mass of the object. If the sun were compressed into a black hole, that radius would be about 3 kilometers. Gravitational waves are another significant discovery. Einstein predicted the existence of gravitational waves in 1916, and in 2015, LIGO directly detected gravitational waves from the merger of two black holes over 1 billion light-years away. The waveforms observed matched the predictions of general relativity. All these phenomena show that gravity is not an external pulling force. It is geometry moving through space-time. This form of gravity tightens the relationship between laws of motion and inevitability. If space-time has a certain structure, then motion will naturally follow that structure. The motion of objects is not the result of any imposed command. It is simply the outcome of the structure of space-time. The question then becomes clearer. Why does space-time adhere to these geometric relationships? Why does curvature respond to energy in this way? Could there be other geometries that exist? In any case, general relativity has provided us with a profound insight into how physics is intertwined with the structure of space-time. Gravity is geometry. Motion is guided by curvature. The fabric of reality is not a backdrop. It is part of the law itself. The universe is an incredibly intricate system, and the existence of life seems to be no mere coincidence. However, what we call the anthropic principle suggests that the existence of physical constants within a range that allows life is not surprising. The truth is, only those conditions that can support the existence of an observer can be observed. This is not evidence that the universe was designed for life, but rather a selection effect. We can only perceive the conditions in which we are able to exist. Yet, a deeper question remains unanswered. Can the constants in the universe change, in principle, or have they been bound by a deeper mathematical necessity, a fundamental requirement in the structure of the universe? In some theories, these constants are not random at all. They may arise from symmetry breaking or from boundary conditions set at extremely high energy scales. Grand unified theory and string theory hypothesize that these constants may converge to a single value at very high energy levels. In string theory, extra spatial dimensions and geometric configurations may determine the values of these constants through the mechanism of compactification. However, to date, no experimentally verified theory has been able to predict all the parameters of the standard model. These constant values are still just inputs for experiments, not results of a theory. This raises an intriguing question about the possibility of alternative physical laws. Can we imagine a universe with different constants, or even different numbers of spatial dimensions? In some theoretical frameworks, these alternative choices can exist mathematically. For example, if the number of spatial dimensions were different, the laws of gravity and electromagnetism would also change. In a three-dimensional universe, the inverse square law arises from geometric calculations. But in a four-dimensional universe, gravity would decrease according to the cube of the distance, rather than the square, affecting the stability of planetary orbits. These conclusions suggest that there may be structural features of the universe that are tightly constrained by its own geometry. However, other parameters may allow for broader variation. The cosmological constant is another example. In the late 1990s, observations of supernovae showed that the universe is expanding at an accelerating rate. A simple explanation in general relativity is that the cosmological constant is a very small positive number. The small value of this constant is what allows structure to form in the universe. If the cosmological constant were larger, the universe would expand too quickly for matter to clump together into galaxies. If it were negative, the universe could quickly collapse. The strange thing is that the value of the cosmological constant lies within a very narrow range, allowing for structure formation, creating an intriguing condition regarding the fine-tuning of constants in the universe. The big question remains whether these constants can change. One cautious approach is to acknowledge that our current knowledge is still incomplete. Some parameters that seem random may eventually be explained by a deeper theory. What seems random today may become necessary in the future. Another possibility is that these constants are not unique throughout the entire universe. The multiverse hypothesis could be a direction where each sub-universe might have different physical constants arising from symmetry breaking in different regions of spacetime. In some models of cosmic inflation, different regions of spacetime may experience symmetry breaking in different ways, creating locally different constants. String theory also suggests that different vacuum states may correspond to different effective theorems. In these scenarios, the constants we observe in our universe might reflect local conditions rather than universal necessity. The multiverse hypothesis expands the theoretical space, but finding experimental evidence remains a major challenge. Questions about the inevitability and randomness of physical laws are not only matters of physics, but also of philosophy, inviting reflection on the limits of explanation and the potential changes in the universe. This theory opens up a larger space for exploration. If alternative choices exist in mathematical theories, are the physical laws we observe just one reality among many? Or if they are uniquely determined by a deeper structure, would this necessity be even more profound? This question is sure to continue to arise. When we combine the theory of eternal inflation with a vast vacuum landscape, a scenario of the multiverse emerges. In such a universe, there could be different regions of spacetime with differing constants and physical laws. In each bubble universe, constants could vary, and in some universes, delicate structure constants could have different values, or symmetry breaking could create different particle spectra. However, it is important to emphasize that these ideas remain speculative. There is no solid experimental foundation for them. Cosmic inflation has received strong experimental support for some of its predictions, but eternal inflation has yet to be directly tested. Meanwhile, the string theory landscape is still a theoretical framework that has not been proven through experiments. Experiments at the CERN Large Hadron Collider have not detected evidence of supersymmetry or extra dimensions, which are often linked to the theoretical frameworks of string theory. Since bubble universes in the multiverse cannot directly communicate, this limits the practical ability to observe other universes. This is a major challenge for direct verification. Nevertheless, the multiverse hypothesis still attracts attention because it could explain the fine-tuning of physical constants in our universe. If multiple universes exist with different parameters, it is not surprising that at least some universes might have constants that fall within a range that supports life and structure. This raises a fundamental question. Why do these laws exist? Thanks to the multiverse hypothesis, this question is reframed from "Why do these laws exist?" to "Why do these laws exist here?" The multiverse theory doesn't eliminate the question of the existence of physical laws but redefines the question from uniqueness to selection. However, this redefinition does not erase deeper questions. Another important question still remains. Why does the universe have such a structure? Why did inflation happen? What is the landscape of constants like? And even, could there be other constants or structures in another universe? These questions elevate us to a new level of reflection on the existence of physical laws. Nonetheless, the multiverse theory is still hypothetical and lacks experimental evidence to prove it. However, it expands the scope of research, creating space for larger questions about the inevitability of physical structures. Instead of asking why these laws exist, we begin to ask why there is a mechanism that generates many different, effective descriptions in the universe. While multiverse theories and string theory are still in development, they provide an interesting theoretical framework for explaining why physical constants have the values they do. However, the question of the existence of physical laws has yet to be fully answered. When a hypothesis is extended in this way, one question remains. Does the existence of the multiverse erase or clarify our curiosity about the existence of legal structures? These questions do not have easy answers, but it is precisely these questions that drive the ongoing search for why the universe has this structure rather than another. One of the standout ideas in modern physics comes from John Archibald Wheeler, who summed up his theory with 3 simple words: it from bit. He suggested that physical reality, what we call it, might arise from information, specifically from bits. Wheeler, who spent his life studying relativity theory, black hole physics, and quantum theory, observed that in quantum mechanics, the act of measurement plays a crucial role. When information is available, results become clear and predictable. From there, he began to suspect that information is not merely a description of reality but might actually be the fundamental building block, constituting everything in the universe. To understand this idea, we need to return to the information theory developed by Claude Shannon in 1948, where information is defined as the reduction of uncertainty. Shannon's entropy formula can be understood simply as the idea that if a message has many possible outcomes, receiving that message reduces the uncertainty about what that message will convey. This formula has a special feature. When measuring the uncertainty of possible outcomes, it directly ties into thermodynamics. Both Shannon and Ludwig Boltzmann, in their entropy formulas, measure the number of possibilities that constraints can produce, clearly and precisely. A prominent application of this concept of entropy appears in black hole physics. In the 1970s, Jacob Bekenstein proposed that black holes have an amount of entropy proportional to the area of their event horizon. Stephen Hawking later showed that black holes emit thermal radiation due to quantum effects near the horizon. From this, the idea of the holographic principle was born, developed by Gerard Hooft and Leonard Susskind. They proposed that the information describing a space can be encoded on its surface rather than inside the space itself. These ideas suggest the possibility that space-time geometry and gravitational dynamics could arise from deeper informational constraints, rather than being independent phenomena. Along with quantum mechanics, this creates a tight link between quantum systems and space-time geometry. Researchers in quantum information theory are now exploring the relationship between quantum entanglement, entropy, and space-time geometry in theoretical models. One of the more interesting theories is digital physics, where Edward Fredkin and Stephen Wolfram suggested that the universe could be a discrete system, processed according to simple computational rules. This opens up the possibility that space-time and matter might emerge from fundamental information processes. However, string theory, with its theoretical capability of extra spatial dimensions and various vacuum states, raises a bigger question. In 1997, Juan Maldacena developed the ADS-CFT correspondence, a theory that suggests a gravitational theory in high-dimensional spacetime could be equivalent to a quantum field theory without gravity in low-dimensional spacetime. All these ideas invite us to reflect on the foundational nature of information and its connection to physical laws. When information could be the fundamental element, physical laws are no longer simply external rules, but could arise from informational constraints, creating a universe that is both ambiguous and tightly structured. Looking at the universe through the lens of information, everything becomes more intriguing than ever. What we once considered to be eternal forces in nature could simply be manifestations of a complex network of information. Imagine that space and time, traditionally understood through geometric models, could actually be emergent properties of quantum information. If spacetime can be translated through the binding structure of information, then perhaps it is information itself that creates geometry. This shifts how we view the laws of physics. Instead of asking why certain equations govern fields and forces, we could ask a different question. What constraints are necessary for the processing of information to occur consistently? When some transformations of information are prohibited, symmetries may emerge. If entropy must increase in closed systems, time, as a symmetry, might emerge as an inevitable result. This way of thinking provides a fresh perspective. The speed of light is not just the limit of motion, but also the limit of information transfer. Quantum uncertainty could reflect limits on the simultaneous knowledge of additional variables. The universe, instead of being a machine governed by rigid forces, might be a network of informational relationships where everything is maintained by consistency. However, whether this viewpoint is the ultimate foundation or merely a metaphor is still an open question. Some physicists argue that information is a useful description laid upon deeper physical entities, while others suspect that it might be the fundamental element itself. Regardless, the increasing importance of information in modern theoretical physics is undeniable. From black hole entropy to quantum computing, the concepts of information have permeated fundamental discussions about the universe. If laws emerge from informational constraints, the very existence of laws might reflect deeper requirements for a consistent informational structure. The universe must be internally consistent, avoiding contradictions and maintaining certain informational balances. In some ways, laws may not arise from commands but from consistency. This concept of information also sheds light on something about time. Time feels to have a distinct direction. Memories flow to the past, expectations pour into the future. Cold stones melt in warm rooms, and scrambled eggs never return to their original shape. This is the familiar sensation of time passing that everyone easily perceives. However, many fundamental physical theorems are symmetric in time. Newton's equations of motion, Maxwell's equations, and even Schrödinger's equation in quantum mechanics remain valid if time is reversed. But the second law of thermodynamics stands out. This law clearly asserts that in a closed system, entropy never decreases. While entropy is often described as a measure of disorder, it actually measures the number of possible microstates that can exist in a given macrostate. States with order are less likely to rearrange into microstates, while chaotic states have countless possible configurations. This limitation is quite clear. If a box contains gas and a barrier is removed, the gas will spread throughout the box. The microstate arrangements where the gas is evenly distributed have an extremely large number compared to the scenario where the gas is trapped in one corner. This process is almost certain to occur, while the reverse process, trapping the gas, though not prohibited, is extremely unlikely in a practical time frame. This explanation was clarified by Ludwig Boltzmann in the 19th century. He tried to show that thermodynamic behavior could be explained by the movement of individual molecules. His H theorem demonstrated that a quantity related to entropy tends to decrease over time, leading to an increase in entropy in thermodynamic systems. This understanding shows that the arrow of time doesn't arise from fundamental equations but from statistical considerations combined with boundary conditions. On the microscopic level, equations allow processes to occur in both directions. But, at the macroscopic level, high entropy states dominate and push time in a certain direction. It is entropy that creates the asymmetry of time. In the universe, time is not an arbitrary addition to physical equations. It arises from statistical structures, from probabilities, and initial conditions. The microscopic equations of nature are time-symmetric, meaning they can go both ways. But when we look at macroscopic behavior, that changes. It is then that we realize that the laws of physics are not merely descriptions of static relationships, they also govern the changes over time. It is this change, with a clear direction, that reflects deeper statistical constraints. The universe unfolds in such a way that the future cannot be the same as the past. And this difference is not random, but is a consequence of the structure of entropy and probability. This issue brings us to an unavoidable question in any profound discussion. Why is there this structure? Why these particular physical laws and not others? This leads to what philosophers call the explanation regress for every answer. There is always another question. Why is there this symmetry? Why the deeper mathematical consistency? Each answer opens up a chain of new questions. And then the question comes back. Why this law? And so, the chain of explanations continues. One way to address this chain is to find a fundamental principle, a principle from which everything can emerge, and perhaps end the chain of explanation at a necessary point. This is the driving force behind unified theories in physics. If all forces and particles arise from a common foundation, then perhaps the chain of explanation would stop there. But another possibility is that the explanation must stop at some point, and there may be features of reality that cannot be explained further. They simply exist. The philosopher Bertrand Russell expressed such a view in his discussions about the existence of the universe. When asked why there is something rather than nothing, Russell answered that the universe might be a brute fact, meaning it exists without requiring further explanation. Applying this perspective to a physical law could suggest that some laws might be brute facts, not derivable from deeper principles. They could be the foundation of reality. This does not mean abandoning explanation. In fact, it simply acknowledges that there might be limits to explanation. It is important to distinguish between scientific explanation and metaphysical explanation. Scientific explanation operates within the framework of empirical studies. It seeks mechanisms, predictive models, and mathematical structures that explain observed phenomena. On the other hand, metaphysical explanation asks why these laws exist. It seeks the reason for the existence of the very framework of those laws. When general relativity explains the motion of Mercury's orbit, it does so by applying a geometric law to a measurable situation. But when the question shifts to why the strong force has its particular coupling constant, or why space-time has 4 dimensions instead of 3 or 5, the question becomes more ambiguous and enters the realm of metaphysics. The history of science may indicate that sometimes deep explanations are not possible, just as Newton treated gravity as a force without explaining its mechanism. Later, Einstein provided a geometric description, and what was once considered fundamental was re-explained. However, even Einstein's equations may not be the final layer. And there is a caution in logic. The chain of explanations cannot simply continue indefinitely. If each law requires a deeper law for explanation, and the deeper law requires another, then the chain of explanations would never end. At some point, either explanation will stop, or it will circle back to consistency. Self-consistency may be the stopping point of this chain. It is possible that the deepest structure of reality is a complete and non-contradictory mathematical system. From this viewpoint, the universe exists as a logical structure and does not require further explanation. In modern physics, the structural relationships between electric and magnetic fields continue to form the foundation of our understanding of reality. However, scientific progress not only helps us understand the inner nature of particles like electrons or quarks or spacetime, but it also reveals a network of relationships connecting measurable quantities. From here, we see two main forms of structural realism, a perspective in the philosophy of science. Epistemic structural realism asserts that only structure is knowable, even though objects may possess intrinsic properties beyond our ability to access them. But Platonic structural realism goes further. This viewpoint holds that structure is everything, and that no independent existence exists outside the relationships that objects participate in. This idea resonates strongly with modern physical theories. For example, in quantum field theory, particles are not isolated entities. They are excitations of fundamental fields. Their properties do not come from a hidden substance inside them, but from how they interact with electromagnetic fields, how they respond to weak interactions, and how they transform under symmetry operations. In general relativity, the geometry of spacetime is not a passive stage. It dynamically interacts with matter and energy. The curvature of spacetime depends on the distribution of energy and momentum. The structure of relationships between events determines motion. Quantum entanglement pushes this idea of connectedness even further. Two particles can exhibit correlations that cannot be explained by their independent intrinsic properties. The shared state of the system contains linked information that determines the measurable outcomes. The properties of the system cannot be reduced to the properties of its individual components. In light of structural realism, physical laws are not imposed upon independent objects existing separately, but are the models of relationships that form the essence of those objects. Laws are not merely commands applied to objects. They are patterns of relationships. Equations do not simply describe how objects behave, but are networks of relationships that constitute their essence. This perspective reduces metaphysical tension, because if laws are commands applied to independent objects, we would have to ask who enforces them. If laws are merely descriptions of independent objects, we would then need to explain why they behave consistently. Structural realism completely alters this question. There are no isolated objects awaiting governance. From the start, there is a relational structure. Consistency is built right into that structure. We no longer need to ask why this structure behaves consistently. It's like asking why Euclidean geometry maintains its angles. Those angles are part of its essence. However, this does not entirely eliminate mystery. One can still ask why this relational structure exists instead of another. Nonetheless, the need for external enforcement fades. Laws become expressions of structural consistency. In mathematics, the sum of the angles in a Euclidean triangle is 180 degrees, and this property is not imposed from outside, but arises from the structure of Euclidean space itself. Similarly, some physical behaviors may follow necessary rules arising from the relational structure of fields and symmetries. Modern theoretical physics increasingly emphasizes symmetry groups, topological invariance, and geometric relationships. The language here is the language of relationships, not material. Fields interact through structured connections. Particles transform under symmetry operations. The curvature of space-time encodes gravitational interactions. This perspective opens the way for a broader synthesis. If relational structure is foundational, then physical laws may not be different from that very structure. The question of why laws exist becomes closely tied to the question of why structural consistency exists. The universe might not be a collection of objects following rules. It could be a set of structured relationships, which inherently have certain laws. Within this framework, laws and structure are not two separate entities. They are two views of the same underlying order. The concept of chaos in physics and mathematics carries a much more precise meaning than in everyday life. In physics, chaos is not the absence of laws, but rather the behavior of systems that are extremely sensitive to initial conditions. Such systems follow deterministic equations at each moment, but the unpredictability arises from this sensitivity. The universe we live in is not a completely chaotic world. In fact, the universe displays dynamics with clear structure. The chaotic systems we know, such as in meteorology or dynamics, while unpredictable, still exist within a framework of strict rules. The uncertainty in these systems is not the absence of laws but arises from the nonlinear interactions of the components within the system. Chaos does not replace laws. It operates within certain rules. To understand this better, we can imagine a universe where every event occurs without any stable patterns. In such a world, stars could flicker randomly, chemical bonds could form and break without any statistical patterns, and even memories could be impossible. However, the real universe reveals a layered order at smaller scales. Quantum probabilities follow tightly constrained distributions, and at larger scales, classical mechanics governs motion with predictable accuracy in many contexts. This shows that stability is not the absence of fluctuations but the presence of a consistent structure. A stable solar system can exist even with small gravitational perturbations introducing chaotic elements over billions of years. Earth's climate may change unpredictably from day to day, but long-term energy balance is still maintained by thermodynamic constraints. The coexistence of order and unpredictability suggests that laws are the framework in which complexity unfolds. Chaos does not eliminate laws, it exists within them. This suggests a shift in how we view physical laws. Physical laws are not commands imposed upon independent objects, but rather patterns of relationships that form the essence of those objects. We cannot understand laws as immutable commands. They are temporary models, formed through continuous observation, measurement, and validation. Science is not just about collecting and observing data. Scientific laws do not naturally arise from observation. Data can be disordered, incomplete, and imperfect, and thus, the scientific method provides a structure to explain it. Karl Popper, a 20th century philosopher of science, emphasized the possibility of falsification in scientific theories. According to Popper, a scientific statement must be testable in a way that it can be proven false. A statement that encompasses all possible outcomes would not provide a constraint on reality, and therefore cannot be considered a scientific law. Laws like Newton's or Maxwell's are not absolute truths. They have been tested through countless experiments. However, they always have limits to their scope of application. For example, Newton's equations are still accurate in situations involving normal speeds and gravitational forces. We continuously test and look for anomalies, much like scientists searching for deviations in modern physical models, such as the electron magnetic moment experiment at Fermilab. Each anomaly opens the possibility for adjustment, increasing the precision of models. All of this reflects an important principle. The laws in science are temporary models. They are not absolute statements but the best descriptions based on current evidence. This adjustment process is a collaborative effort not only of scientists but also of institutions, peer reviews, and technological development. Observations not only confirm laws but also bind them, limiting speculation and narrowing theoretical possibilities. When asking whether physical laws are necessary, the question shifts to the realms of possibility, necessity, and contingency in philosophy. Physical laws, therefore, are not absolute truths but descriptions of unified patterns in the natural world, always open to testing and refinement. The universe we live in is not a completely chaotic world. In fact, the universe displays clear structural dynamics. Chaotic systems we know, such as in meteorology or dynamics, while unpredictable, still exist within a framework of strict rules. The uncertainty in these systems is not the absence of laws, but arises from the nonlinear interactions of the components within the system. Chaos does not replace laws, it operates within certain rules. To better understand this, we can imagine a universe where every event happens without any stable patterns. In such a world, stars might flicker randomly, chemical bonds might form and break without any statistical patterns, and even memories might be impossible. However, the real universe reveals a layered order at smaller scales. Quantum probabilities follow tightly constrained distributions, and at larger scales, classical mechanics governs motion with predictable accuracy in many contexts. This suggests that stability is not the absence of fluctuations, but the presence of a consistent structure. A stable solar system can exist even with small gravitational perturbations introducing chaotic elements over billions of years. Earth's climate might change unpredictably from day to day, but long-term energy balance is still maintained by thermodynamic constraints. The coexistence of order and unpredictability suggests that laws are the framework in which complexity unfolds. Chaos does not eliminate laws, it exists within them. This leads to a shift in how we perceive physical laws. Physical laws are not commands imposed on independent objects. They are patterns of relationships that form the essence of those objects. We cannot understand laws as immutable commands. They are temporary models, formed through continuous observation, measurement, and validation. Science is not just about collecting and observing data. Scientific laws do not naturally arise from observation. Data can be disordered, incomplete, and imperfect, and thus, the scientific method provides a structure to explain it. Karl Popper, a 20th century philosopher of science, emphasized the possibility of falsification in scientific theories. According to Popper, a scientific statement must be testable in a way that it can be proven false. A statement that encompasses all possible outcomes would not provide a constraint on reality and therefore cannot be considered a scientific law. Laws like Newton's or Maxwell's are not absolute truths. They have been tested through countless experiments. However, they always have limits to their scope of application. For example, Newton's equations are still accurate in situations involving normal speeds and gravitational forces. We continuously test and look for anomalies, much like scientists searching for deviations in modern physical models, such as the electron magnetic moment experiment at Fermilab. Each anomaly opens the possibility for adjustment, increasing the precision of models. All of this reflects an important principle. The laws in science are temporary models. They are not absolute statements, but the best descriptions based on current evidence. This adjustment process is a collaborative effort not only of scientists but also of institutions, peer reviews, and technological development. Observations not only confirm laws but also bind them, limiting speculation and narrowing theoretical possibilities. When asking whether physical laws are necessary, the question shifts to the realms of possibility, necessity, and contingency in philosophy. Physical laws, therefore, are not absolute truths but descriptions of unified patterns in the natural world, always open to testing and refinement. Stars shine because nuclear physics operates stably. Galaxies rotate according to gravitational dynamics. Black holes merge and emit gravitational waves detectable by instruments on Earth. Each of these phenomena reflects stable underlying relationships. The existence of laws does not diminish the mystery of the universe. Rather, it frames it. Laws create a structure within which deeper questions can arise. This universe could have unfolded differently in ways we can only speculate, but it is not chaotic in the sense of lacking pattern. It is coherent. Within that coherence lies both explanation and wonder. The laws are not separate from reality. They are expressions of its structure, and within that structure, thought itself becomes possible. The question that started this journey was simple in form, but vast in scope. Why do physical laws exist at all? Along this journey, patterns have emerged. Laws describe consistent regularities in nature. Symmetry connects conservation principles to invariance. Geometry shapes gravity. Quantum mechanics encodes probabilities with remarkable precision. Statistical mechanics shows how order and disorder unfold over time. Information theory suggests that structure itself may be foundational. Each perspective deepens our understanding, yet none closes the inquiry completely. What we know with confidence is that the universe behaves in stable, mathematically describable ways across enormous scales. The same gravitational dynamics that govern the Moon's orbit also govern distant galaxies. The same quantum principles that define atomic spectra in laboratories apply to the formation of stars. Conservation laws hold true wherever they are tested, regardless of where they are observed. These regularities are not fragile or local. They extend across billions of light years and billions of years of cosmic history. What we also know is that many laws are connected to deeper structural principles. Symmetry explains conservation. Geometry explains gravity. Statistical reasoning explains entropy increase. Quantum field theory explains a vast array of particle interactions through gauge invariance and field dynamics. These are not arbitrary collections of rules. They form an interconnected network. What remains open is whether this network is ultimately necessary or contingent. It is not yet clear whether the values of physical constants are uniquely determined by deeper mathematics or represent one realization among many possibilities. The multiverse hypothesis offers one speculative path. Structural realism offers another philosophical lens. Informational approaches suggest that consistency constraints may lie beneath familiar laws. The limits of explanation remain clear. For every layer of understanding, a deeper question can often be posed. Why symmetry? Why mathematics? Why structure at all? Yet the persistence of these questions does not signal failure. It sharpens inquiry. It encourages clarity about what science explains and what lies beyond its current reach. Asking why laws exist refines scientific thinking. It prevents complacency. It reminds us that equations are not just computational tools but reflections of stable patterns. This draws attention to the conditions that make prediction possible and understanding meaningful. There is also a quiet humility in recognizing that some aspects of reality may resist further reduction. The universe may contain foundational features that admit no deeper derivation, or it may reveal further structure in time. Calm curiosity is the appropriate stance here. The existence of laws is not a dramatic anomaly requiring urgent resolution. It is the steady background condition for all that is familiar. It allows stars to shine consistently. It permits chemistry to organize into complexity. It enables memory, measurement, and reflection. Living within such a universe means inhabiting a reality where patterns persist long enough to be discovered. It means that observation can accumulate into knowledge. It means that mathematics can map onto experience with striking accuracy. The question of why laws exist does not diminish this stability. It illuminates it. Perhaps the deepest insight is not that laws demand explanation, but that they make explanation possible. Without regularity, there would be no science, no inference, no reasoning from past to future. The universe does not appear chaotic in the sense of lacking structure. It appears coherent, and in that quiet coherence, the pursuit of inquiry continues.